Hi, let's look at a couple of examples of Kirchhoff's voltage law. In this first example, you can see that we have a voltage source that's driving 3 resistors, and so we're going to want to go around the perimeter of this circuit. Now, I like to go from the bottom left-hand corner. I like to go clockwise. Certainly that's not required by Kirchhoff's voltage law. It's just a personal convention that I have. So you can choose whatever convention it is that you would like to use, but that's the one that I tend to use. So as I'm starting at point D and going vertically up toward point A, the first thing that I'm going to encounter is this voltage source. Now, just as a reminder from a previous discussion, remember that the voltage source, as shown here, is going to have positive on the longer side and negative on the shorter side. So what that's going to tell us is that when we encounter this negative sign right here, that means that the voltage source is going to be negative in our KVL equation. So over here, I'm going to go ahead and write a KVL equation, and I'm going to start off by writing negative 30 in there. And again, the reason for the negative sign is that because when I first encountered the voltage source, I encountered the negative terminal first. Now, when I come to the passive devices, I know that the current is going to be flowing into the positive terminal. The way that they're labeled, you can see that I encounter the positive terminal of that one first, then the positive terminal of this one first, and then the positive terminal of this one first. And so I'm going to be able to go ahead and write each of those quantities with positive signs. So I'm going to write plus 12, and then I'm going to write plus V sub R2, and I'm going to write plus 8 is equal to 0. And so then I can solve this equation for VR2. VR2 is going to be 30 minus 12 minus 8, which it turns out is 10 volts. And then furthermore, we were also asked to find the current I around each of the circuits. Since I now know V sub R2 is 10 volts, I can calculate I, because if I know this voltage, VR2, and if I know the resistance that accompanies it, then I can easily calculate the current by using Ohm's law. Notice that I can't use the R1 or the R3 because I don't know those resistor values. Of course, once I find the current, I could calculate those resistors, but I'm not asked to do that. So the current, which has to be the same around the entire circuit, that same current is flowing around the entire circuit because there's no other place that the current could go. I is equal to V sub R2 divided by 10 ohms. And we just found that V sub R2 is 10 volts. So this is 10 volts divided by 10 ohms, and this will yield 1 amp. So there was an awful lot of unknown information in that circuit, and just by a simple application of Kirchhoff's voltage law, we were able to find the voltage VR2 as well as the current. The most important thing to remember, though, is why we would choose to use the positive and the negative signs for each of those terms, and it's based on whichever sign we encounter first when we are traversing the circuit. Okay, let's tackle this problem. You can see now that the voltage source is put in the opposite direction, so the positive terminals on the bottom and the negative terminals on the top. Once again, I'm going to start in the bottom left-hand corner and I'm going to go clockwise, but once again, you don't have to do that. That's my personal preference. So as I'm doing that, I'm going to encounter the positive terminal here first. So I'm going to write for KVL, I'm going to write that 12 is going to be my first term. Then I'm going to encounter the negative sign on the 3 volts, so this is minus 3. I'm going to encounter the negative sign on the 5 volts, so this is minus 5. And I'm going to encounter the negative sign on VR3, so this is minus VR3. And this has to be equal to 0. So therefore, VR3, if I move that over to the other side, this becomes 12 minus 3 minus 5, which is equal to 4 volts. And it's positive, therefore VR3 was drawn with the correct polarity when it was originally drawn. But of course, we didn't really have any way of knowing whether VR3 was going to be positive on the left or positive on the right. We just happened to get lucky in this case. Now we're looking for the current that's going around this circuit. Well, once again, we now know VR3, and we also know this 8 ohm resistance here. So therefore, the current is VR3 divided by 8 ohms, and this is equal to 4 volts divided by 8 ohms, which is 0.5 amps, or as any good electrical and computer engineer would probably prefer to write this, that's 500 milliamps. So hopefully this pair of examples has helped you to understand how Kirchhoff's voltage law can be used to solve relatively complicated circuits. I know these seem complicated now. Trust me that in just a couple more lessons you'll be tackling problems that are way more complicated than this.